move on to the last topic I was going to talk about today. So this was another problem that was posed to a student, the same student I was working with my other dilation problems, and it is basically we're given, it's similar to the problem we saw in the vertical dilation video, where we have two functions. Let's call our red function f of x and our green function g of x. And what our goal is to take our red function and transform it into our green function. So let's take what we've learned about dilation and apply it to this problem. So first of all, let's look at some points. So we kind of saw before, we don't want to just start shifting things. So let's observe some points before we start applying things to our problem. So we'll notice that this time I've actually color-coded our points. So we want to shift this point to here, this point to here, and this point to here, along with all of our other points, obviously, on these lines. But these are just 3 key points I kind of picked out to just look at because they're nice, nice numbers. So let's go ahead and bring up what these are. Okay. So let's kind of observe what's going on here. So from here, so we want to go from here to here. So our x-coordinate here is -2, and our x-coordinate here is -4. So it looks like to go from here to here, we would just multiply by 2. And to go from here to here, it looks like we're just multiplying by 1/2. So let's see if that's true in other places. So if we look at these 2 points, to go from here to here, remember we're going from red to green. 3 to 6, we'd multiply by 2. And to go from -4 to -2, we'd multiply by 1/2. And we also see that's true for our orange points. To go from 5 to 10, we would multiply by 2. And to go from -2 to -1, this -2, no, this -2 to this -1, we multiply by 1/2. So it seems like we're both doing a vertical and a horizontal dilation, and that's exactly what's going on here. And there's no real trick to it, so what we're just going to do is we're going to both vertically dilate our graph and horizontally dilate our graph. So let's go right down and see what that would look like. So oops, okay, just a pen. Alright, so remember our red function was f of x, and our green function was g of x. So to get g of x to equal f of x, so we'll prep this. So we know for a vertical dilation, we need to put our f of x in parentheses and multiply all of our f of x by whatever we're vertically dilating our function by. And we know for a horizontal dilation, we want to multiply all of our x-coordinates by whatever number we're horizontally dilating by. So let's first look at our vertical dilation, since that's pretty straightforward. So we notice to go from here to here, and from here to here, from here to here, it was 1/2. And we remember that when we vertically dilate, all we have to do is just simply plug in what the factor is between our points. So we're vertically dilating by 1/2. So we'll just go ahead and plug in 1/2 here. And so now we want to think about our horizontal dilation. So this one's just has one extra step we need to consider. So to go from here to here, we need to double, right? Go from 3 to 6, it's times 2. To go from -2 to 4, it's times 2. To go from 5 to 10, it's times 2. But remember that we don't just want to put a 2 in here. If we put a 2 in this spot right here, that would be wrong. And just to remind you why that is, so say we had y equals x squared plus 1. And I'll just use the same example as before. So say we plugged in 3, we would find that y equaled 10. But when, say we horizontally dilated it by 2, oops, let me use a different color for that. And this is not related. This is just kind of an aside, just to remind you how horizontal dilation works. Whoops. So, say we're going to horizontally dilate it by 2. Remember, what that does to the x-coordinates is it doesn't double them, it actually halves them. So if we wanted y to still be 10, since we don't want to mess with our y-coordinates, we're just looking at moving our x-coordinates now. Yeah, let's just look at this real quick. So we have 9 equals 2x squared, and we have 3 equals 2x, and we have 3 has x. So yeah, so notice our x here was 3, and our x here is 3 halves. So if we want to go, whatever we're trying to multiply, so since we need to multiply all of our x-coordinates by 2, we actually don't want to put a 2 in here. We want to put the reciprocal of 2. We want to put in 1/2. And it's kind of just for the opposite reason that it was here. So when we put in the 2, it basically halved the value of the the x-coordinate. So to double the size of our x-coordinates, you'd want to multiply by 1/2. So yeah, so this is actually, I believe, would be our answer to this problem. And if you kind of want to see, you feel like you want more sort of proof that this is our right answer, I actually went ahead and figured out the lines that are being used here. So if we just, let's ignore the, not the green lines, but the second half of these lines. Shut these points off. And we just look at these 2 parts of the line. Notice that our original equation here is negative x minus 1. So let's go ahead and write that, let's go ahead and write that here. So we have our original equation being y equals negative x minus 1. And we have this equation, the equation for this line right here, is negative 1/4 x minus 1/2. X minus 1/2. Okay, so what do we have to do to turn our y equals x minus 1 into this y equals negative 1/4 x minus 1/2? Well, theoretically, if this is the right answer, we would just apply this x squared f. We would just apply, sorry, I realize you can't see my cursor. We should just be able to apply this formula to this function, and it should, if this is correct, it should give us this. So let's go ahead and try that. Let's do 1/2 times by all of this, but instead of x, we're going to have 1/2 x. Minus 1. And again, I'm sorry for the diagonal here. Equals y. Now let's see what this equals. So 1/2 times negative 1/2 is negative 1/4 x, and then 1/2 times negative 1 is negative 1/2. And we see that this problem here, or this function here, sorry, is the same as this one here. So it kind of just gives you a little more maybe reassurance that this is the right way to go. This is the right sort of formula to translate f of x into g of x. And I hope that these 3 videos about dilation will have helped you sort of comprehend the subject better. And have a good day.